G'day, Michael here. This video is about how to create and design something like this, which is fairly simple, really, but with OpenSCAD, and how I go about, building out the logic for it. There are two parts to any design with OpenSCAD, and that is obviously the shape that you want to achieve. And in this case, this is kind of a very simple bracket designed to hold a PVC pipe for a grow bed for aquaponics. That is basically a generic sort of a slot to rest onto steel tubing or whatever, or even a flat surface. It doesn't matter. It's basically designed as a kind of a locating clasp setup for holding this in place. So I can fix this to like a rack, kind of a ladder of tubing, and the holes there are basically to use cable ties. So yeah, it's a pretty basic, simple part, but nonetheless we have things like the rounded or filleted corners this way and that way. We have the fact that this is not a regular shape, it's kind of fundamentally a trapezoidal shape with cutouts in them. And we've got an octagon here, octagonal cutout. We've got obviously a circular style cutout, and we've got these rounds here. Now you can see here on the screen the resolution. So I guess what I'll be covering in this video is how to control that resolution, how to achieve these beautiful fillets and things so that we've got rounded surfaces, how to achieve this octagonal cutout, how to create this trapezoidal shape, and I'll be showing a system called, well, a method called HOWTO, which is kind of like lofting, but it's kind of also like shrink wrapping something. Yeah, beautiful tool, very useful. And another one called Minkowski. Now Minkowski is a very cool piece of software, I guess, but it's a very cool piece of logic. And that's all available to OpenSCAD. Now you can see this is the design. It's fairly, it's not just squares. So this is all the code that's required to create that design. That's it. Now I will be going through how I built this design. In fact, I'll build it from scratch with this gone. So I'll do it, the hard way, and you can see me make, the fumbles I make, etc. But you'll see me build a design. So perhaps that may help you build your design if you're going to try and use OpenSCAD. Now I found myself in a position where I'm using OpenSCAD more and more, and that is, there's two reasons for that really. One is the fact that being open source, my files are mine, whereas you use proprietary software, you lose your files if you don't maintain your license. So that's one really big appeal. But really the biggest appeal for this is not so much that as the fact that with a small parameter change I can make this a different design. So let's just have a look at this to see what I'm talking about. Now that's looking like that, so this is our reference, right? It's the same part. If I change the diameter of pipe to say, I don't know, 70, and get it to regenerate that, it completely regenerates the design. It'll be a completely different shape, and you'll see how different shortly. Well, one day when it gets there. There is a bit of a nuisance. I wish there was a way of working around it, but I can't see how that would be achieved, and that is, I'll get our system monitor around here where we can see it. It basically works one CPU core flat out to do the work, because it has to read the instructions like sequentially. So that's kind of a downside of how this works. Whereas if you've got like a pointy clicky program, it's got all the various items as separate, they're kind of dead shapes. Whereas this is an active thought process, and obviously you've got to think of this and sort that problem out before you move on to the next problem, and then sort that out, and so on. And so you've got the downside of it having to use one CPU core. Actually, I'll move my head a little bit down the road. Move that guy. Yeah, where are we? Oh. My head right out of the road. You down there. So this will give you an idea how busy my computer's working. Now, the reason why I'm wanting to show this is so you can see when the machine is busy. I tend to like having the system monitor running so I can see what the computer's up to. Right, now if it wasn't for the screen recording, basically all the CPU cores would be pretty much idle right now. So a lot of this sort of dancing of the CPU usage is because you're seeing this video. But once, if you're working on your own machine, a decent single core performance computer will actually do quite a good job with this. This computer is a dual Xeon. I'm just running it not with hyperthreading. I'm just running it so the 12 cores are running without hyperthreading, so it's 12 threads as well. Alright, now you can see here the segments showing up in these curves. On VariCAD, which is my graphical environment program, you don't have any control over the resolution. So whatever the compromises are it makes, that's what you get. And you'll find that to be the case with most graphical programs. I've got higher and lower precision settings on a VariCAD, but that's about it. There's no absolute control. Now if we look at this design, is it this one? You can see there the segments involved with making it. But I think, where are we now? Is it this one? Yes. Now here you can see how shells are actually created. Now that's inverted there and you can kind of see through it, so it's an awkward way to look at it, but you're able to see what's going on sort of through the shape. So it's handy for certain things. But what is of interest to me, I'll just move this over here, is all these other little triangles and things here. Now initially it didn't look like that. It looked like, where are we now? That. So it doesn't look like there's anything going on here. But regardless of whatever program you're using, this goes on. So if you're getting errors with using, say, a slicing program, it may well be stemming from errors in these items. Funny enough, the errors I tend to get on OpenSCAD is actually on OpenSCAD's display, not in the final job. Whereas other programs I've had it, so the CAD program shows a perfect result, but then I go into a slicer and it's broken somehow. But where those breakages happen, where you see if you're running a slicer and it says, oh, repair these errors or whatever, it's usually as a result of these kind of parts having some flaw in the calculation. Now, why do these parts exist? You might ask, but it's basically this. Every shape can only be determined by triangles. And if you've got facets here, like you can see, that would be a trapezoidal shape split in two as a triangle. Now those 2 points have to connect to something to make it a triangle too. So every line segment where it comes together on a vertice means it can't go into a shape that's not a triangle. So if it's like a hexagon or something going into a circle, there may be a very differing number of segments. Well, actually, just this, you've got a straight line here, right? That's one segment, and here you've got a whole lot of different segments. Now, there's no way you could have all of these segments going to just the same outside thing, vertices, and have a triangle. So it has to all be broken up into triangles, and that is basically the problem you'll have with creating 3D models if you're having breakages. It's this business here. If there's some errors in a calculation, also the calculation tolerances of one program might be more forgiving. So if it's out by a micron or something, it might be okay with one program, and another program might see it as a gap. So each program's got its own idea of what's an acceptable range, and that's why you tend to have these repairs. There are some parameters on the Prusa slicer for what is considered the same point and what's considered different points. I can't remember what they call it, but yeah, there is some configuration in a Prusa slicer, for argument's sake, for that, and I suspect all the other slicers too. Right, so I thought I'd cover that because I want to show you how to solve all of that, and also it's worth noting that, I don't know whether that'll show up, you can see the segments in the print here. Now this is done with a 0.6mm nozzle and 0.2mm layer height, but you can see it really is almost focused. I can't quite get it to focus. Anyway, I can feel like facets there, and you can see facets there but that's with this very low number of facets. So if I wanted to make it like totally invisible, I could double the number of facets there, and it would be invisible. But if you don't need a whole lot of facets on a design, there's no reason to add them, because basically you're adding a whole lot of information to the design, which obviously takes the computer itself longer to generate that. Also, it makes the files larger, and it takes longer, obviously, for anything to be processed on a slicer. And then if you've got a lot of segments, it can actually cause pauses in the printer. So that's another parameter you might have in the slicer, where you can cut down how many segments it creates. I think they work on like an angular change and a distance travelled. But if you notice your printer is like printing then just sort of pausing a lot on something, it's basically there's too much information going at the printer, so too much for it to process. Yeah, so I think that's enough about that. But it's important to know, this is our destination. These are some of the issues. So let's look at another reason why I use OpenSCAD, and because that may be of use to you as well. I'm steadily moving more and more towards OpenSCAD for some other features too. Now, that's it there. It says down here on the bottom edge here, 931 out of 1,000. Well, I'm not quite sure why they do it that way, but to my mind, I think of it as like 93.1% instead of 931 out of 1,000. Okay, so on this backside, we've got this surface has to match like a corrugated iron detail like you might have in a shed or a roof or something like that. Right, on this side, I turn off that so it's a bit less cluttered. Whoops. And you can see I've got actually recessed or engraved fonts, if you like, with the design. And you can see I've got a couple of screw holes. The corners are tapered and rounded. You've got a bore size. So you've got a bore size, you've got fonts, you've got the whole shape is tapered, and you've got the corrugate. That's all achieved, including the text, with that there. To get this corrugate profile, I've used a DXF file, which is here. Where are we now? It's from I've used linear extrude, import, yada yada. So this line here creates a block. Let's just run corrugate so you see what corrugate does. I'll just enable that. Now here you see the first little tip that I have. In this corner here, I might just zoom in so it's a bit easier to read for you guys. You probably want to have an HD monitor at least to watch this video. Don't try it on your phone in case you haven't worked that out already. These are what's called modules, right? Now I've deliberately created a whole heap of modules, and in that I have sort of a bite-sized chunk of what goes on in this design. And a module that I've called main, which is kind of borrowing a convention out of like C programming language or other programming languages where you've got like main. But here I'm running it as a module, not as main, if that makes sense. And at the top here, I've got calling a module. Right, I'm going to call corrugate, so I'll just run that now. And this is what the corrugate module does. That's this one here, which loads that design. Now, I'll disable corrugate again by just commenting it out. 2 forward slashes commented. If I run main, what does main do? Main does the difference between the backing and the holes. Like there's backing and there's a hole. So this is kind of, in a way, the whole program, kind of. But let's go further than that. This main is just asking the difference between a backing and our holes. So let's see what the backing looks like before it's taken away the holes. So let's just enable the backing. And you can see that is what I'm calling the backing. So it's this sort of trapezoidal kind of radius corner, tapered doodacky here. Now what is backing anyway? Okay, now it uses this hull command. So backing is this guy here. It does that. Okay, so how's that done? I'll disable that. Let's have a look at... Oh no, leave the backing enabled. What I might do is just see what the hull is doing. I'll just take that out. So here I'm working on the module backing. Right. Now just simply put that bracket on the next line. That's a trick I make if I want to comment out, say, this command. opening and closing bracket just contains stuff, but it's not in itself anything. So if I go F6 now, you'll see that I've got 4 cones. Now I'm in the way, so I'll get out of the road. So you've got 4 cones. Now those 4 cones are only kind of used for the outside extremities by the function hull. So let's run that, and you'll see the difference between hull. So it's those 4 cones, and the hull is kind of like a shrink wrap around the outside. But it always goes to the furthest one. Right, so if I do, let's just bump one of those up a different amount. So one of them is going to stick up, so let's do that, see what happens. So I've lifted that one up 10 millimeters, and you can see how it's reduced that twist, right? Or if I made its length T plus 10, you can see it's basically shrink wrapped to all of that. And you've got up here, like I said, it's to the extremities, so we've got this little flat surface of it being higher. So it doesn't go to the far edge, it goes to whatever sticks out the most from that hull shape. Now that's important. It's not quite the same as a loft, but it actually lets you do some other tricks that lofts can't do. I also find this is 100% reliable. I've had trouble with lofting on other programs, but I've had zero trouble with hulls. They always work. So there's some inherent reliability you get out of OpenSCAD that you don't necessarily get out of other programs. If something's wrong, it's guaranteed to be something you've done. It's very rarely anything to do with actual programming of having a flaw. The other thing is I found that this teaches, as I showed you earlier, all those facets. I didn't know about all those facets until I used OpenSCAD, and I could pull apart the logic behind how the triangles all work. So with the triangular shell creation that you have with any of these 3D programs, a lot of it you're blindfolded to. You're kind of shown the outer look of it rather than all the points. Now Blender's quite good if you want to have a look at wireframes of, say, another CAD program. Import your STL file with Blender, and you can look at the actual the triangles, the facets that go up to making a design. So quite often you can repair really bad STL files with Blender. Now OpenSCAD can import DXF files, and it can import STL files, and it can even use like bitmaps. Like if you have shades of grey, can indicate the depth of something. So there are a lot of things you can do with OpenSCAD. But anyhow, this video is not about all of that. It's going to be about how to create this and how to build the logic in behind it. And I'm going to do it from scratch. I mean, I've done it once, so I'm going to be a little bit more kind of mentally prepared for how to do it. But the result is that I'll still make mistakes, and you'll still see how I overcome them. I hope I make some typing mistakes and some syntax errors, which no doubt I will. Things like that, so you can see what sorts of things to look for if you have the same syntax errors and you can't seem to get on top of it. Right, so the first thing I have to say with OpenSCAD when you are building a design is to think about what you are going to add and what you are going to take away. Because this, as you saw even with this design, the hull was created from those 4 cones. So you put the 4 cones in and then use hull to build that out. Right? And the other shapes, the holes, etc., were actually solid objects taken away. So I'll just show you the holes. Let's just disable that. Let's have a look at the holes that were reduced from this part, taken away from this part. Okay, so the holes constituted the corrugate. These, well, they're cylinders but with a low number of segments, and these solid lumps of text in space. And those parts were all subtracted from the backing. And we saw the backing a minute ago. It was the bit made out of the hull from the cones. Alright, so that's how as a primary thing, that's what I do. I build something and take other things away. And I tend to call things body or backing or base or something like that as the main thing. and holes, whatever gets cut out of it. Now, that's this design. The other thing that I will show too, I've got another design, and that is this guy. And if you pay attention, this is almost identical to the other design, because basically I made the other design from this one. You can see it's a very different part, but in essence the recipe is the same. That what's changed between these two designs is what revolves around the fonts. The other fonts were, let me just go there, that one. These other fonts were sort of sprayed around the corners. On this guy, they're all in a row centered on the design. The other difference is these hole centers vary and the overall dimension of the part varies. So there's really, in essence, they're identical designs. And so with OpenSCAD, they are identical design, barring basically these parameters and a bit of the font formatting down the text formatting. So they're the two parts that are different. So pay attention to this. I'll just zoom in a tad so it's a little bit easier to see. Look at this, and that, and this, and that, and this. Basically, it's the same design. Whereas on a lot of CAD programs, it'd be probably borderline easier to make it new rather than edit it. You know, it's one of those sorts of things. Also, if you find you're 1/2 millimeter out with the bore size, you change the bore size 1/2 millimeter, and it's redesigned. So yeah, it's good for like tuning, fine tuning an error in your design, as well as major changes. So fine tuning and major changes are very good in OpenSCAD. Okay, so let's just close all this stuff. Close without saving because I don't want that changed. Now here's our original. What I've done, except you saw how that dimension changed. I better put that back to what it was so I don't have a problem. Control save, F6, there we go. Right, now I'm going to close that, so I'm going to be blindfolded, starting from scratch. So how do we open this? What do we do? OpenSCAD, new. Suppose I should save it. I'll save as. I'll go to documents in this case, it's just a dummy. So you've got to give it some sort of name. It's easy to just, if you start creating a design, just save it before you've even got any content, and that way you've automatically got your backups and so forth on that. Okay, so what do we have? Looking at this guy here, we've got that pipe, which is 110. So I'm going to make a variable. I'll just call it pipe because that's how it works in my head. 110. That'll do. So I'll just zoom in so you can see what I'm typing. The graphics is not that important. Okay, so the next line, what have we got? This cutout. I'm going to call it tube because that's for the tube. It's 40. Let's see the radius on the corners, which I'm just going to go RAD because the less typing there is, the better as far as I'm concerned. Equals, I don't know, 5. That's arbitrary. It has no bearing on anything. It just makes these corners pleasant. And I'll kind of use that for everything. You'll see what I mean in a minute. Alright, so we have that. The next thing we have is the block size, right? Now the two parts that I really need to, well actually three. We've got the thickness, we've got the overall width, and then we've got the height. Now the height will be determined by the diameter of this pipe and the diameter of this cutout. Now this is going to be from a cylinder, right? This octagonal shape is going to be from a cylinder. Now this part I produced actually yesterday. The 3D printer can just cope with this overhang. It's about its limit. So I can get away with that 22.5 degree angle or whatever that is, right? We also want to have these holes radiused out. But what I want to do is I'm going to use a function called Minkowski, which adds one design to another. So I'll just show you what that means. Okay, let's just do that. Minkowski. This is not in the design. This is just so you can see it. Open brackets, close. Actually, I might put the bracket on the next line. It's worthwhile keeping your indents so that whatever is inside something else kind of follows some logic there. Okay, so let's do a cube. 50. Yep, close semicolon. Might disable Minkowski for a second. So you can see how easy it is to disable something if you're trying to test out a design. So let's just see that. And I'll just there's a 50mm cube. It's 50 this way, it's 50 in height, and it's 50 in depth. Right, so that's our cube. Now what I want to do is use the Minkowski function and add a sphere of 10mm. So let's do sphere diameter equals 10. Oops. D, that'd be good. And let's have 8 segments in it. So string fn equals 8. I don't know why they use that convention, but that's what they do. So here we are. Semicolon. So let's just have a look at those two designs. Okay, so it's got a kind of octagonal sphere shaped thing, right? Now if I change that to 18, you can see there's more segments. So we can do that to see what it looks like. Right, but now that I want to, this is what's important to know, and this is why I'm trying to explain this function. What it will be doing, if you can imagine this sphere being slid along the corners of that cube, and then that kind of being shrink wrapped, like a hull type thing. That's what the outcome will be. So this cube here is going to grow by the diameter of the sphere. It's going to be below 0 by half the sphere, and it's going to be above 50 by half the sphere. So if you watch this grow, I'm just going to enable Minkowski. Here we go, F6, and it'll just bubble out. There you go. So it is bigger by the radius of that sphere here. It's bigger by the radius of the sphere there, and bigger by the radius of the sphere here. And it is also the same on the opposite side. So the cube is now 60mm, which is the size of the cube plus the size of the sphere, but with the rounded corners of the sphere. So we're going to use that to create this rounded shape. Okay, but to create the trapezoidal shape, I'm going to be using a series of cylinders with a hole. But we have to remember that design is going to be smaller by whatever we use for the sphere to add to it. So we're making kind of, if you take off these radiuses or radii in every axis, that's the design we want to create, and then we're going to add the round to it, just like we've done with this cube. So it's important to understand how that works. Alright, now this gets really very mind-boggling very quickly, so I'm going to try and show you how I achieve, and probably everyone else for that matter, achieves a way of dealing with everything in a chunk that you can handle. So what we'll do is we'll just make a module, we'll call it body. Okay, and the purpose of that body is to create the block that we're going to make. Now you saw I did open and close brackets. So the syntax is the word module, a space, whatever we want to call it, this pair of parentheses. Now the parentheses are set up in such a way you can pass information into the module, and the other word pass, P-A-R-S-E, is so the module will sort of separate out from that block of information various parameters you might want to insert into it. So you might have 5 or 6 variables, or maybe 20 or whatever, that you can pass to the module that basically get only used from there on locally within the module. Right, whatever's described outside the module, those variables, like you can call these items, I've used pipe, tube and radius, that's for my head, but we could call this one Q and that one Z and this one P. It doesn't matter. They're just names that suit me and hopefully help suit you. Now I've also used capitals like capital RAD because all the commands on OpenSCAD are all lowercase, so I'm sure that I'm not going to be using like a command instead of a variable name. So by doing that, it's quite useful. The other thing I would do, if I've got a number of different radiuses, I might go underscore, let's say big, so the big radius, and there might be a little radius or whatever it is you want to do, but I'm using the underscore to generate a space to my eye, but it's actually a continuous character to the scripting. So kind of cheating by the fact of how our eyes and brains work versus how the scripting works. So I'll get rid of that again because I don't want to type all that all the time. So keeping the variable names short as is practical helps you a lot for typing, but you may need a certain number of characters to say enough that you can remember what it is. Alright, so enough waving hands around. Right, body. We're going to use the command hull. So I'm going to go hull, open close, open curly brackets. Since I go close curly brackets, you notice that bracket is in line with the command above it, just like that bracket was. But if I go next line, the brackets will be in line with their command. So these belong with that. And you can see these two brackets are highlighted, so whichever one I'm on, it highlights the other. So that makes it a very useful, you're trying to debug where you're at, you can see that one highlighted the one above it, etc. So this business here about them highlighting does help with clarity. Now I just went new line or enter, and it's indented me. Now if we're chopping and changing, you might find that your indents don't actually work out right, so it's worthwhile editing to keep the indents logical. Now it's important, really, it's important to do this stuff that I'm telling you about right now, because it's very easy for these to get not very clear. So, okay, so here we are ready to do our first item in the hull. I might just get rid of all of this because it's of no use to us anymore. Right, so we're doing our first thing called body. So with creating the body, we want to have kind of our core shape, the size of what this would be without the added, the added sphere to it, like we had in this cube. So we want to have, like the original cube was, in this shape before the Minkowski function. So I want to have increased radius shapes on the corners to make this quite round, and I'm going to kind of cheat a little bit and make like a double radius. So what I'm going to do is, you saw on that previous design where I used 4 cones to sort of peg out the shape. Well, here I'm going to use 4 cylinders. So I'll get like a cylinder here and a cylinder here and a cylinder here and a cylinder here, and just do a hull around that. So it ends up being this trapezoidal shape, less all these radii from the corners. Okay, so let's just do that. So we have to know what the size of that block is. Alright, so we need to have body underscore h for height, right, is going to have to be pipe divided by 2. So it's half the height of this pipe. We want a little bit past that line, so let's go maybe plus 10. So that's a 10 mil above the center of the pipe, and between here, the two sort of intersecting cutouts, I want 10 millimeters there too. So I can just change it to plus 20, or we can leave it to plus 10 if you want to kind of memorize that it's separate, because you might have like 10 plus 15, or you can do it that way, or you might actually name another variable and use another variable for one of those numbers, or both of them, or whatever. That. But we've also got this tube on half of that, right? So that divided by 2. Does that make sense? So what we can do is put cube up here, so it's plus cube. We have to put that in parentheses, so it's going to do that calculation first. Now that's important with basically, or any program really. Most programs do what's called mathematical order, proper mathematical order. I'm only doing that for us to see it. Semicolon denotes the end of the line. Okay, so we've got, you can see how the colours have worked. We've got the name that I've used is in black, the equals is in blue, a number is in like sort of a red colour, and the semicolon's back in blue again. And you can see the convention is carried through again and again throughout. And where we've used the word module, it's come up as the green, etc. So a lot of elements are color coded, or what they call syntax highlighted. In the editor, actually helps you keep track of whether you've, well, number one, what kind of things it sees it as, and number two, helps things work for clarity for you. So, right, so that's our body height. Now the body width, sorry, is down here. I just nominated a width of 180. It doesn't matter. It's just an arbitrary thing. I could nominate some other size. Oops, have an equals in there. Yep. And the body underscore T, that's the thickness, equals, I think I just made that an arbitrary number of 60. It was just opinion, so it didn't matter. Right, there's that. Now that's the final size, so we really have to take off the radius twice. So it's minus rad times 2. Minus rad times 2. So that'll give us our size less that radius top and bottom, or left and right, whichever way we're looking at it. Okay, so if I do that, right, and it has to be less rad times 2. So it's important that rad happen before these variables so that they will be done correctly. Because otherwise rad would have no value. Okay. Cool. So now we're going to do our first, like our primitive, which is going to be cylinder. Now cylinder has, there's a number of different ways of using cylinders. Now probably, if you're looking for any help, I find the easiest thing is just use the cheat sheet. So here's the cheat sheet, and if we wanted to look up cylinder, let's just have a look at that. You can see there's two. You can see there are two kind of ways of using it. One is just a simple cylinder where it has one diameter, or one where you can use, a taper. You can even make a cone with it. Right. So I'm only just going to use, in this case, one shape, and you can use D for diameter, or you can use R for radius, and R equals RAD. That's our little thing, comma, the height, H, equals body underscore T, which is this number here, and what I might do is, so that I don't have to mess around with changing resolutions, string FN is the magic number for the number of facets, the facet number. I don't know why I use string FN. Anyway, here we are. And I'm going to use a variable called res, which I've just named. Right, so I better go put that up the top so it knows what to do. Equals, I don't know, let's try, I don't know, 8. Let's just do that. Semicolon. And I might just disable hold for a second. So we just see what I've created. Well, nothing, because I haven't called the module body. So everything inside module will be basically ignored unless we call upon it. So body, semicolon. So that's actually now going to be called upon. F6. Okay, so that's how we created that. I think I'd like a bit more than 8 segments. Let's just try bumping that up to maybe, I don't know, 12. Is that better? 16. 16, yep, F6. Okay, that's probably a good facet number. Yeah, that'll work. But you can see that's centered at 0, 0, 0, like 0x, which is, let me just get this right. It'll be Y. So X, oh yeah, here we go. If you look down here, you've got the 3 colors. There's X going in this way, Y going front to back, and Z goes vertically. Now, to get this so it's centered in all 3 axes, we use like a parameter called center. We go equals true. So F6. So that's nicely centered on that location. Now, you can see how we've got curly brackets here to define like the beginning and the end of a block of things to do. We can do also the same thing as a one-liner, but we are limited to what can be included on one line. I'm going to use a command called translate, and that is to move things around. So you're moving it, trans being move. Late. Translate. We're going to go, when we're using 3 dimensions, like in strictly X, Y, Z, in OpenSCAD, we open the parentheses, then we open the square bracket, and this seems to be consistent syntax across the commands. Okay, so are we going to move something in x-axis? Yes, we are. We're going to go BODY underscore W, but only half that divided by 2. Nothing Y, nothing in the Z, close square bracket, close parentheses, space. So I do that right now, F6. It's moved over in the x-axis. But we need to go also in the y-axis, and we should go maybe negative body underscore H. So do that again. You can see that's moved that way. Oh, we've got to divide that by 2. Sorry. Okay, so F6. So looking at that from above, you can see it's sort of off to one side. So that's kind of equivalent to maybe this corner, right? We need to do the other corner. So let's do that. Might just squeeze that out a bit further. Might also reduce the font size. If you're not using a high resolution monitor to view this, I think this is going to be pretty difficult for you to follow. So, but you'll want to use a high resolution monitor on a computer anyway. So I'm kind of going to hand that responsibility off to you. So I'm going to delete, insert, insert. Now you can see the indent didn't work perfectly there because I did a copy paste and I didn't have the right indents sort of to copy. Okay, so there we have that. And all I have to do is make one of them negative, go minus. Okay, so we have both the left and the right like corners. Now the top here is going to be different width, so we have to work that out. Let's go do that. Now there are 2 bits that I want to have there, and that is this tip either side. That helps to determine, oops, the tip either side here determines like the top of the shape. So well, let's just use those 2 variables, that sounds fair. Tip equals, I'm going to cheat and go rad times 2, and the top is going to be equal to the pipe diameter plus 2 tips, so tip times 2, semicolon, pipe plus tip times 2. That sounds reasonable, so let's just do that. I'm going to just do a really simple cheat. and I'm going to go, should be able to just make that top, yeah? No. Wrong spot, here we go. Top. And instead of going negative in the y-axis, I'm going to go positive in the y-axis. Okay, that's better. It's seeing that as one line. I haven't pressed the return key apparently, so I better do that. Okay. That should be right, I think. Let's go. What have I done? Some syntax error. What have I got wrong? And there's a bracket missing. Or parentheses more accurately. 6. Okay, what have I got wrong there? One of those has to be negative. Alright, here we go. F6. Okay, so there's our shape there. Well, kind of like staking out the 4 corners of the trapezium. Now if we do the hull, we get the shrink wrap happening. There we go, so we've got our little shrink wrap thing going on. Okay, now we want to use Minkowski, the Minkowski function, to add a sphere of the radius. So let's do that. And here's where the first example of the the indents being wrong, because that's where the hull should be, which means all our indents are out by 1 tab. And I'm going to reduce the font size just to make it a bit clearer again, and I'm running out of text space. Close, and so that's the hull bracket, that's the Minkowski bracket, and that is the module bracket. Okay, so after the hull and before closing the Minkowski, we have to go sphere r equals rad, comma, string fn equals res, capital R. Is that right? F6. Yes, that looks believable. So we've got that part done. But actually we need to get these holes in here, and these holes have to be rounded the same way. So what we're going to have to do is make the holes in here. So we have to work on our before our Minkowski function. Just, yeah, that's right. I'm going to disable that for a second. So 2 forward slashes, you might notice, comments it out, and it becomes that cyan colour that you saw there. Alright, so we're going to disable the Minkowski, so we're looking back at the original trapezoidal shape. We've got to get those 2 holes in there. Right, so now those holes are for straps, so I'm going to cheat and go, actually, TRAP equals 10, but I've got to add the radius to the holes, because when we do the Minkowski it's going to reduce by the radius. So rad times 2 semicolon, so we've got 2 of the radiuses added to the hole size, so it's going to be making the hole bigger, and we need to get, let's just disable that for a second, and we're going to go get a module, what I'm going to call it, tie down, that'll do, open, and basically we're going to be making 2 cylinders, so I'm just going to cheat and borrow those 2. Just to save a bit of bother, and I'm just going to change this number to a number that looks about right. And the radius is going to be No, it's actually the diameter is going to be the strap. So I'll change that to D, because we're going to use the cylinder using the D parameter instead of the R parameter, so the diameter parameter instead of the radius parameter. And we're going to call it strap. Height equals the body thickness, but I might go plus 100, so it's definitely big enough. This will make sense in a second. What we're going to be doing is using these cylinders to punch a hole through this body so as to create that hole, right? So this hole here is what we're making. That sounds fair enough. I'll just get that there. T plus 100, and we'll make D equals strap. D equals this time plus 60 minus 10. I'm not sure I saved much by copying and pasting here, but here we go. Is that right? Tie down. So I'll just call the tie down with nothing else, F6. So there's our two holes occurring in space. If I do body and tie down, that's what we end up with. But if I do it this way, so hull, okay, we're going to have to add another function in here, and that's going to be difference. And again, we're out by a tab. It looks like I'm going to be wrestling the line feed versus the indents for the whole time. Right, so that's the hole. Well, so we've got the hole, and then we've got to run the module tie down. So just explain that in a second. Semicolon. Zoom out again. Okay, so this is what messed with my head when I started with OpenSCAD. You do something, but what you do to it happens before in your text, but it's kind of like moving out bracket for bracket for bracket for bracket. So what you do first is the bit inside. Here's the first bit that gets done, and then what we're going to do to that is hull that design together. And what we're going to do after we've hulled that design together, which is that trapezoidal shape, we're going to use the difference thing between all of that and the tie down. Now the tie down were those two like cylinders, so we're going to use difference to take away the tie down from that hull. That makes sense. So I'll just run that. We'll cut out the tie down. So we're just running the body, and we've got those two holes missing, right? And then we're going to enable the Minkowski here. So Minkowski is going to be applied to that. That'll take a bit of time. Okay, so now we've got, the primary block with the corners radiused. If we want higher resolution than that, which we can do, but we probably don't need it. If you want to bump that up to a higher resolution, go ahead, if that's what you're going to do. Not that I think you'll be designing this particular block, but if you do, go ahead, just as an exercise, that's fine. But now what we've got to do is cut that from it, and we're going to cut this from it. Now this is an octagon shape, and that's basically intended to be a cylinder. You can see I've picked a fairly low resolution because it's not that critical that it's perfectly round. A pipe's going to be resting in there, and you basically don't see that. So it's pretty simple to do that. Let's just do exactly that. We're going to make a new module called holes. Holes. Open bracket, that's correct. Close bracket. So what we want to do is a cylinder the size of that pipe. Cylinder, open. D equals pipe. comma, h equals block underscore t, which is the block thickness, plus plenty, which is just going to make it plus 100. So that's that, semicolon. So I might just disable body. And we're just going to look at holes. Oh, that's not very good. What have I done wrong? I've got an error. Block T, no, body T. Silly me. Now, when it doesn't get a value that makes any sense, OpenSCAD has some basic, working parameters. Most of them seem to result back to like 1. If it can't make sense of it, it just says, well, that value is just 1, so you've got something instead of nothing. So that's how it gets around some of the errors. So if you end up with this sort of business happening, then there's chances are there's something wrong with dimension. This is supposed to look more like that. And we also want to have it centered. Center, that is right. Equals true. Zoom out. So this big hole here, or it's a big cylinder I should say more accurately. If we wanted to change the resolution, I'd probably make this one on the spot. We can go 64, let's say. That's what that looks like. Yeah, so that, whatever you want to do for that accuracy or just the segmenting, whatever it is you want to do, you can do that. Now, when we do the octagon, we're going to use that same feature. So just keep an eye on how useful that string FN is. Alright, so we need to move it out the half the block height minus that 10 millimeters, which is one of these numbers here. Okay, so we're going to go translate, open square bracket, so it's nothing in the X. Hopefully it's positive. Yeah, I think it's positive. So body, I should say, keep saying block body underscore h divided by 2 less 10. Is that right? It's 10. Comma 0. Close square bracket, close parentheses, space. That looks feasible. I might just run the body just so I can see it anyway. That looks feasible. Okay, now the next one, we've got basically the same kind of thing. No, I'll write it from scratch just so we can go through the process. I'll turn off body again. Cylinder. Now we've got another set of issues with that. Oops. The cylinder equals the diameter will equal the tube variable. Get that out correctly. Comma h equals body underscore w, which is the width of the body, plus 100 just to be sure. But this time we're going to go string fn equals 8. So by doing that, we're going to get an octagon out of this. We'll just see what this does. But it's going to be, we don't want it. So I'm going to go center equals true. Right, so we've got that guy sitting there in the wrong orientation. We need to lay it flat. So let's do that. So rotate, open parentheses, start square brackets. We're not going to rotate around the x-axis. We're going to rotate around the y-axis, I think. Let's just do that. So it's 0, 90, nothing around the z-axis. 0, close, space. I think that's right. Let's just go. What have I done wrong? And close the square bracket. Okay, so that's it there. I think that's right. And then I've got to Might run the body so I can see that I've got the right orientation. Yes, the right orientation. Now I've got to move it. Translate. Oops. Open square bracket. Nothing in the X, 0. In the Y, it's going to be body H divided by 2. Now we're going to have a negative, so it's going to be minus the body H divided by 2. Just run at that just to check my thinking to there, but we'll probably be out of position by the size of that radius, so let's just do that. What have I done wrong? Didn't close the square brackets, and I have got the wrong number of variables. 6. Okay, so we've got the radius from the original block setting. Okay, so that'll be wrong here too. Now, let me just go through that again. Going back to our original shape, I'll disable the Minkowski so we can see that. Okay, so the block height and block width was to that center line. So I've actually grown by radius that way. Yeah. So, yeah. Make sure I'm okay. So our block height and block width are to these edges, and you can see we're out of place there by that amount. Minus radius. Okay, so that's actually an error here. How I staked out the original block is not quite right. That is minus rad, because it's a negative number. Go plus rad. Plus rad minus rad. Okay, that's the wrong way around. That's also a negative number, so it's plus rad. So obviously, if we're going minus the body, or minus a number, to have less minus, you have to add the radius. Just mathematically it works out that way. Alright, top divided by 2 minus rad. Minus top divided by 2 is plus rad. This is both cases positive, so minus rad. Minus, thank you. Minus rad. So I had a fairly substantial error just then. So let's just see how this all cooks. Okay, that's what I'm expecting it to have been behaving like. So I had an error in my layout there. And as you can see, there's these two parts will be very close to colliding. I'll just turn off the body so we can see how they interact. So something's wrong here with that placement of that cylinder. Body divided. Got something wrong here. Those two cylinders are too close together. They're supposed to be 10 millimeters apart. So what have I done wrong? See ya. That's better. That needs to go out by radius as well because we've got, yeah, that's right. Okay, so we do that as well. So it's that plus rad. Right. Because we've taken away 2 radii, we need to go up radius here and down radius there, which makes sense. So get rid of that body. We should have a 10 millimeter gap between those two parts if I'm right. that looks to be a 10mm gap based on these lines here. So I'm going to just roll with that for the moment, see how we go. Right, so I'm going to re-enable the Minkowski so we can see how that all plays. And I'm going to put the body back on. That looks right, because that's centered on that edge. That's cool. We've got about 10mm down from there. Yep, that's cool. So that looks right. So let's make our new thing called main module. Oopsie. Main, open close, open bracket, close bracket. And this time, pardon me, we're going to go difference, close bracket, close bracket, body. So we go body and holes. So comment these guys out. But if I don't do anything, it'll just render nothing. Just to show you what that's done, nothing. So I actually have to call main, so I'll do that. MAIN semicolon. So now this will be calling main. So again, that's basically at the moment our whole program. Calls these other modules, which are whatever they are. So by breaking the design down into modules, we've got the ability to have every part, every process testable. And there we have our design. Yep, that looks good. And all being well, we should be able to change our number to, like, I don't know, 70, like we did before. F6, and it should still play nice. And so if you need to have something that might have 20 or 30 different parameter changes, by building a design like this, you end up having that time saved of your changes. Also, if you find that a dimension is slightly wrong, it'll rethink based on that slightly different size. Okay, so you can see it's changed completely the block shape to have a smaller pipe, and it's still captured by the same sort of 10mm. We've still got the same notch cut out the back. If you had extreme cases, you might want these holes to float around a little bit, so you might want to do some calculations to determine where those holes go. But this is right for most of the things I'm likely to do with it. Alright, so I'll go Control Z, undo, and I might actually save it. Go F6 to redo that. Now again, if we want to see higher resolution, let's just do that. Let's make that, I don't know, 32. This will take a while to render. No, I'll just get out of there. Now, doubled the number of segments by that resolution number, but that applies in every axis. So I've got a hunch it's going to quadruple the number of points, which also means sort of quadrupling the amount of work the computer's got to do. So it took a while before, it's going to take 4 times that while, and it's going to make the file 4 times larger if I save it as STL, etc. So I'll be 32 in this circle, and 4/8 of 32, so it'll be 8 per the 90 degrees. So it's 8 times 32 rectangles here. Let's just actually do a calculation, make sure my brain's not going to let us down. Oh, it's over here. Bring it to hand. So 8 times 32, 256. Now it's actually triangles, but twice as many, so times 2. Right, so there's 512 triangles. That's just in this one little bit here. And then we've got yeah, there's 3 points in a triangle, so times 3. So I've got, you know, over 1,500 points. 1,500 points. Yeah, they would be separately recorded. So there's 1,536 points just by this little round here, right? Obviously, you can get more and more complex. Yeah, so the numbers can get very large very quickly for the number of points. And of course, when your slicer comes along to slice it, actually, let's just save it and slice it. Let's just do that. Let's just go to desktop, will be fine. Test SDL. The slicer handy. There we go. Okay, so there's our STL file we've just created. Let's slice it. Get my skull out of the road a bit. Now this is set for a 0.4mm tip. If we had a 0.6mm tip, let's say 0.6, which is what I've actually got these days, 2:1 on this printer. Settings, later. Okay, slice now. Light attract. It's not quite the same as this one that I printed, but it's got a bit in common with it. Alright, so that would be the design. There appears to be no errors in the slicing, and as you can see, the slicing turns out pretty smooth. Now, you might end up wanting to drop that resolution down, depending on how things work for you. But yeah, in any case, with OpenSCAD, you do have the ability to make it exactly what you need it to be. If you need it finer resolution, go ahead. If you don't need it that high, it's easy to just have it lower. Alright, well I think that's about all I can do with this. Yeah, feel free to like, share, subscribe, ask a question, leave a comment. Bye for now.